Guys, this is Mrs. Upmore. We are going to talk about Newton's third law today. Um, so this is just the very end of the notes, and we're finally to the third law. Okay, so this one you should memorize the wording to, but you actually probably already know it. It is for every action force, there's an equal and opposite reaction force. The important thing is that it's an action force and a reaction force, not just action reaction. Okay, so you might maybe highlight in your notes or do something to draw your attention to the fact that it's an action force and reaction force. Okay, and it actually doesn't really matter which one is action, which one is reaction. So if I push on my hand, this hand pushes, this hand automatically pushes back, right? And it doesn't really matter whether this one's the action or this one's the action. Either way, both are equal and opposite, even if I'm able to move that hand. So if I'm able to push so hard that I move it, it's still an action-reaction force, okay? There are no exceptions at all to this law. And so I think we mentioned in class one day, like if you can punch a hole through the wall and you overcame that normal force, well, first of all, let's think about that. If you punch the wall, it hurts your hand, right? Because the wall has basically punched you back. If you're able to go through it, it's not that the force was unequal, but rather just that the material structurally could withstand that amount of force. Okay, but it's still always equal and opposite action and reaction. Okay, so we've got a little thought question here. If you have ever watched like a Civil War movie or something, you've seen a cannon shoot and you see the cannon recoil just a little bit while the cannonball flies off, right? So why don't they move the same amount if forces are equal and opposite, right? Shouldn't they, if they have equal forces on them, shouldn't they move the same amount? Well, if we think about it, the net force is based on not on the mass and the acceleration of the object. Okay, so in this equation, the net force is the same, right? So we have equal net forces here. We've got a net force on the ball. We have a net force on the cannon. So cannon pushes ball and ball pushes cannon. All right. However, the cannon has a little, or the cannon has a really big mass and the cannonball has a little bitty mass. Okay, so let's remember our old equation, A equals F net over M. Remember the F or the A and the M are inversely related. So that means for the cannon, a really big M means a little bitty acceleration. Okay, and for the cannonball, a little tiny M means a really big acceleration. Okay, so because they have different masses, the force affects them differently. So again, it's the same force. It's an equal and opposite force on both the cannon and the cannonball. But the acceleration, the result of that force is very different based on the masses of them. Okay? If you've ever been to a shooting range, you know that this is true. The gun will recoil a little bit, but the bullet flies, right? And sometimes, depending on the gun might recoil a lot, might knock you over, might bruise your shoulder, or break your collarbone if you're having a hard time holding it correctly. And it's because the force that the gun puts on the bullet to make it fly is put back on the gun, right? So it's coming back with a lot of force. It just happens to be significantly heavier than the bullet, so it's not going to move as much as the bullet does. And that's a good thing, right? Okay, so another thought question. If everything has equal and opposite forces, why don't they all cancel? Why isn't the entire universe in equilibrium, right? What we have to remember here is that as human beings, we have a very finite view of the universe, right? We can only see just a tiny, tiny little bit. So when we look at the ball that we're holding and we drop, we just see the ball fall. We see the earth pulled down, or we are aware that the earth is pulling down on the ball, putting a force on the ball. We're completely unaware of the force that the ball puts back on the earth. And there's no possible way we could notice that. It would be negligible anyway because the earth mass is so much bigger than anything we would drop, right? Even if we're dropping like a bowling ball, the Earth is significantly more massive. So even though the Earth pulls down on the ball and the ball pulls up on the Earth, or the ball hits the Earth and the Earth hits the ball, we're only able to see the action of the ball. Okay, so everything is in equilibrium, but we can't see it. All right. So again, this is just to try to help you kind of conceptualize the idea that this law has no exceptions. So when you're driving along the highway and a little bug smashes against your windshield, the bug put the same force on your windshield as the windshield put on it. However, the bug has a tiny mass, the windshield has a big mass, and so we only see the effects on the bug, right? Its little body cannot withstand that kind of acceleration versus the windshield, which is unaffected basically. Okay, so last but not least, that brings us to some just kind of thinking questions. So you can see in example 1, fist hits the wall hits the fist. Letter A, head bumps ball, so the result is, or the reaction force is ball bumps head. Windshield hits bug, bug hits windshield. Hopefully you're seeing the pattern here. If we go straight down, hand pulls on flower, flower pulls on hand. So when you pick a dandelion, you feel that resistance, right? So your hand is pulling on the dandelion and the dandelion is pulling back on you. Letter G, compressed air pushes balloon surface outward. Balloon pushes air inward. We could go through and do every single one of these, but I don't think you probably need to. Hopefully you're seeing the pattern. Really, the only part that people sometimes struggle with in third law is just remembering that it's just two objects acting on each other. So you don't ever want to introduce a third object, right? For example, like with the ball hits the bat one, this one right here, ball hits bat, or bat hits ball, therefore ball hits bat is the reaction force. It is not ball hits the air. That air would be a third object. Okay, so make sure when you're doing third law, you're always talking about two different objects acting on each other. And then secondly, you have to be a little bit careful because sometimes we try to turn like a free body diagram into an example of Newton's third law, but a free body diagram is just showing forces acting on one object. Third law is always two objects acting on each other. And that's it for our force notes.